sklearn, linear model, LassoLarsCV. Description: LassoLarsCV implements lasso model with least angle regression Lars and cross-validation to find the optimal alpha. It explores a range of alpha values using cross-validation, selecting the alpha that minimizes a chosen metric, typically the mean squared error MSE. Inputs: X a 2D array-like structure containing the independent variables. Each row represents a data sample, and each column represents a feature. Y a 1D array-like structure containing the dependent variable. It should have the same number of rows as the input array X. Outputs: Core a 1D array containing the estimated coefficients for each feature. Intercept: the intercept term of the fitted model. Alpha: the optimal alpha value chosen through cross-validation. Steps: 1. The algorithm iteratively adds features into the model, starting with the feature most correlated with the target variable. 2. In each iteration, it computes the direction of the feature coefficient change and moves along this direction until another feature becomes as correlated with the target as the current feature. 3. The process continues, adding more features and updating the coefficients until a predetermined stopping condition is met, e.g., reaching a maximum number of features or exceeding a specified threshold. 4. Cross-validation is performed with a specified number of folds to evaluate the performance of a model across different alpha values. 5. The alpha value that minimizes the chosen metric, e.g., MSE, is selected as the optimal alpha. Metrics: mean squared error MSE, commonly used to evaluate the performance of linear regression models. R-squared, a metric that measures the proportion of variance in the dependent variable explained by the independent variables. Visualization plots: coefficient path plot. This plot visualizes the evolution of the feature coefficients as the algorithm iteratively adds features. It helps understand the impact of each feature on the model. Alpha vs. MSE plot. This plot shows the MSE values for different alpha values obtained during cross-validation. It allows visualization of the optimal alpha selection process. Fine-tune parameters: CV integer or cross-validation generator object. Number of folds to use for cross-validation. Maxiter: maximum number of iterations for the Lars algorithm. Apes: tolerance for the stopping criterion. Normalize: whether to normalize the input features. Precompute: whether to precompute the gram matrix. Fit intercept: whether to fit the intercept term. Verbose: verbosity level. Uncertainty methods. Confidence intervals. Confidence intervals can be calculated for the coefficients to assess the uncertainty in the estimated values. Challenges and fixes. Challenge 1: overfitting to the training data when the regularization strength is too low. Sample use case that resulted in challenge 1: when the alpha value is very small. The model tends to fit the training data very closely, leading to overfitting. Fixes to challenge 1: increase the regularization strength alpha. Challenge 2: underfitting to the training data when the regularization strength is too high. Sample use case that resulted in challenge 2: when the alpha value is too large. The model might not be able to capture the underlying relationships between the features and the target variable, leading to underfitting. Fixes to challenge 2: decrease the regularization strength alpha.